Welcome to part 3 in our Orbiter tutorial series. This is Tex, and today we're going to learn about aligning our orbital plane and the use of the align plane MFD. Now in the previous part I taught you how to launch the Delta glider and how to get into orbit. And more specifically, we chose a specific launch window so that we could ultimately reach ISS. So we chose a launch window and a launch heading. And while we were launching into orbit, we roughly aligned our orbital plane at the same time. Now, I should mention before I begin that I used the scenario in the Delta Glider folder called Cape Canaveral. And I mentioned the problem with that scenario was that it starts you out in the Delta Glider on one of the landing pads at Cape Canaveral, and that the Delta Glider is not capable of doing a vertical takeoff from the Earth while holding enough propellant on board to reach orbit. So what I had done before I started recording the tutorial is I moved the Delta Glider over to the runway with the scenario editor and filled it up about halfway with propellant. If you don't want to mess with the scenario editor, I had totally forgotten about this, but in the checklist folder there is a scenario called Mission 1 DG to ISS. This is probably going to be the best scenario for you to load if you want to practice going to the ISS and following along with our tutorial here. It even has a detailed instructions here in the scenario description that you could follow along. Now I realize that following along with instructions and text can be difficult, especially if you're struggling with some of the terminology and just grasping orbital mechanics as a beginner. So that's really my motivation behind making these videos. It's something that I always wanted to do and never got around to finishing, but I hope that some people can find these useful, and quite frankly I find them useful because just the act of making them helps me improve, and I'm always learning new things with Orbiter. That's one of the great things about this program. So with that said, I'm going to load our scenario, which I saved, which will pick up right where we left off after we launched into orbit and we circularized the orbit. So the next step is to align the orbital plane, and if you don't already have it targeted over here, of course you can just open the align plane MFD and you be sure to target ISS. As you can see, we do have ISS targeted here. Now when we align our orbital plane in the terms of the orbital elements, it essentially means that we're going to match the two elements between our orbit, between our orbital plane and that of a target, which define the orientation of the orbit in space, and that is the inclination and the longitude of the ascending node. Now again, I would recommend you check out part 1 of the series, which I describe in detail all of the orbital elements and things like the inclination and the longitude of the ascending node and how that applies to orbital mechanics. But at the top of the align plane MFD you can see our inclination, our longitude of the ascending node, and ISS's inclination and its inclination, or its longitude of the ascending node. So the idea is that we want to get all of these two numbers here matched up between us and our target. So we also discussed in the previous part relative inclination, and that is basically just our inclination relative to our target. And again, because we want our inclination to be the same as our target, relative inclination, we want that to be on 0. One thing that I did not discuss, and perhaps I should have in the previous part, is below that is the rate of change, and that is directly correlated to relative inclination. So when we are decreasing relative inclination closer to 0, the rate of change here will show as a negative number. And if we were increasing relative inclination, the rate of change would show as a positive number. Of course, nothing is happening right now because we're in orbit. We're not doing any burns or anything, so the rate of change is shown as 0. But let me just pause this very quickly and hop out of the simulator for just a moment. And I'm going to play this video that I made, the previous part. And you can see that as we're launching here, over on the align plane MFD, you can see relative inclination is decreasing, and look right below it. The rate of change, it's a negative number. It correlates to relative inclination decreasing. I also discussed about, now with the ultimate goal being we want to get relative inclination as close to 0 as possible. But I also discussed if relative inclination reaches the lowest point it can and then begins to increase, we want it to yaw to the left or to the right to prevent relative inclination from increasing and just hold it at that lowest possible point we could. And to do that, I mentioned the line of nodes over here, the descending and the ascending nodes, this line of nodes. I talked about how it was pivoting around on our position and to try and keep that at a 90-degree angle. Let me just find that very quickly here. You can see how it's spinning around right now on our position. And I talked about if we could keep that at a 90-degree angle between our radius vector here, our position, and the line of nodes. If we could keep that 90-degree angle there, that relative inclination would be held at the lowest possible point. Well, it directly correlates to the rate of change. You'll see that as that 90-degree angle happens here, it's almost at 90 degrees. Look at the rate of change. It just hit 0. Now, the reason I use this 90-degree angle reference here is because it's easy for me to see with my peripheral vision while I'm perhaps paying more attention to the surface MFD or the orbit MFD over on the left side. It's easier for me to see that line of nodes pivoting around on my position with just, barely glancing in that direction versus looking at a specific number on the MFD. So I don't know which way you prefer, which way is easier for you, but just understand that it's directly related to that rate of change. So let me hop back in to the simulator and we can unpause. So moving down, what we have here is AN and DN. This is given in an angle. This is the angle between our radius vector and the ascending node and the angle between our radius vector and the descending node. So you can see right here, this is our position and this is our radius vector. So what this is telling us is between our radius vector here and the ascending node, it's 46.2 degrees and decreasing because we are approaching the ascending node. So that just gives us an idea of almost like the distance between us and the ascending node. And if you look at the descending node, the angle is 225 degrees because, of course, between the ascending and the descending node, that would be 180 degrees. And then between there and there, that makes 224 degrees. So that's what that number is telling you. And then below that, we also learned that Tn is the time to the next node counting down in seconds. So again, you can see we're approaching the ascending node, and that's telling us that we're going to reach the ascending node in about 664 seconds. So 660 seconds now until we reach the ascending node. And at the very bottom here, we have estimated thrust in seconds. So this is telling us how long we would have to burn our main engines in order to align our orbital plane with the target at the ascending node and the descending node. Now, because our orbit is pretty much circular, there's no difference between the time. We could do the burn to align our orbital plane at the ascending node or the descending node. Either one would take the same amount of time, only 1.32 seconds. That's very little time because we did such a good job during the launch to get relative inclination so low. So I could choose any one of these. I'll choose the ascending node because that's the next node we're about to cross. What I need to do is I'll speed time up a little bit and get a little closer. But we need to know what direction do we orient the ship to do the burn. That is obviously of importance. Anytime you're going to align your orbital plane, you're going to use one of two autopilots. It's either going to be this one right here with the plus, that's called orbit normal, or it'll be this one here with a minus, that's called orbit anti-normal. Now the way I've always remembered it is when you're approaching the ascending node, so if you're going to align your orbital plane at the ascending node, you would use the anti-normal autopilot. Ascending starts with A, anti starts with A. So that's the way I've always remembered it. If you think backwards, perhaps this might be better for you. If you're going to do it at the ascending node, what does ascending mean? It means to increase, perhaps a positive number. So what's the opposite of that? a negative number, so you would use the minus. And again, at the descending node, you're descending, perhaps a negative number, you'd use a plus. I really don't know which one of those helps you the best. For me, it's always been, if I'm doing the plane alignment at the ascending node, I use the anti-normal autopilot. If it's at the descending node, then I just use the normal autopilot. So since we're going to do it at the ascending node, we'll use the anti-normal autopilot. So I'll go ahead and engage that. We also would like to know, when do we do the burn? Now down here at the bottom, it says kill thrust right now, but it will illuminate and tell us to engage our engines in orbit normal, and then it'll have a plus or a minus after it. When that happens, that is when we do the burn. And the plus or the minus behind it tells us obviously which orientation we want to have the vessel in. But knowing obviously which way to orient the vessel ahead of time is very useful, because we want to have the vessel already oriented and ready to burn by the time this illuminates. So it is kind of important to know that ahead of time, but it will tell you down here if all else fails. The other thing is, because in this case our burn time is so little, it's only just under 1.5 seconds, that it's going to approach very quickly. So it's good to know, because this will not be flashing very long. It's gonna happen like that. It's just going to be in a moment. In every instance, when you do your burn, you will do so when the time to node, counting down in seconds, reaches half of the estimated burn time. So in this instance, we're going to do it at the ascending node, and it's shown as 1.39 seconds of burn time. So when the time to node reaches just over half a second, which is, half of this time, that's when we do the burn. So let me speed time up, and we are within 1 minute of the burn now. 30 seconds, 20 seconds, 10 seconds. Okay, normal time. Let me pause it very quickly. When I unpause this, you're going to see we're at 3 seconds from the burn. So when we're just over half a second to the node, this will illuminate. So because this happens so quickly, I just wanted to pause it. You'll see this will illuminate and it will tell us to burn. That will correlate with what I said with the time to node here. Watch relative inclination. It will drop to 0, and you can see I talked about the rate of change. It will be shown as a negative number as I'm doing the burn, lowering relative inclination. So here we go, and burning. Okay, now what I can do is I can use translation thrusters to clean this up a little bit. So I'm translating forward until we have that 90-degree angle here. Everything's on 0. You have relative inclination on 0, and all estimated thrust time is on 0. So we are perfectly aligned with ISS at this point. So going forward, as far as synchronizing our orbits and everything, it really becomes just a two-dimensional problem. We no longer have to worry about our orbital plane. I should, however, mention that if you have the non-spherical gravity sources enabled, that your orbit will be perturbed somewhat from that. So you'll notice that relative inclination, it just won't stay right on 0, but it should never go above 1 degree. As long as you're under 1 degree, the synchronized MFD will work, and I'll go into detail about that in the next part. But just keep that in mind. If you notice that it's not staying right on 0, don't worry about that. It's probably that non-spherical gravity setting being enabled. Before I leave you, though, let me give you one more example. Now let's say that we want to go to Mir. Let me open the map MFD, and let's change display from ground track to orbit plane again, and target. Very quickly though, let me target ISS. Just as a demonstration, you can see because our orbital plane is perfectly aligned with ISS, you can't even see its orbital plane because ours is laying directly over top of it. So that kind of gives you a graphical demonstration of what it means to have your plane aligned with the target. Now let me target Mir, and wow, see the difference? This is our orbital plane right here, and this is Mir's, and they are drastically different. So that means that's going to take a huge burn if we wanted to align our plane with Mir. And we can confirm that if we come over to the Align Plane MFD and target Mir. and that's telling me that at the ascending node, which here we are approaching the ascending node, if we were to try to align our plane with mirror here at the ascending node, it would take 478.2 seconds, or we could choose to align it over here at the descending node. It would take 477.9 seconds. That is an incredible amount of fuel and time to align our orbital plane. So you can see quickly how planning ahead of time during our launch could save you tons of fuel after you're already in orbit. It just takes so much fuel to align your plane when it's that far off. However, there is one tip that you can consider. If I open the Orbit MFD, and let me just press mode to get rid of those numbers so you can see this a little bit better. You can see this is the line of nodes between the ascending and the descending node, and that correlates directly over here to this dashed line on the Orbit MFD. So this box that's filled in is the ascending node, and this one here is the descending node. If I wanted to decrease the amount of fuel it's going to take to lower our relative inclination to mirror, I could increase the eccentricity of our orbit. In other words, make our orbit from a circular orbit to an elliptical orbit, and that would also impact the amount of fuel, the amount of time it takes to align our plane. Let me just show you what I'm talking about. So here we are. I'm going to coast around to this node here, which is the ascending node. In this case, I could coast around to either one of them. It really doesn't matter because we are in a circular orbit. Let me just coast over here, and I'm going to face prograde. So, okay, so we're facing prograde. We're pretty much over the node. For demonstration purposes, now I'm just going to burn my main engines. And you can see what's happening as I'm burning my main engines over here on this side of the planet. It is increasing our altitude over here on this side of the planet, and eccentricity as a result is increasing, and our orbit is becoming more elliptical. But look what's happening over here. Remember, this is our descending node over here. Correlates with this here. Look at the burn time. It's decreasing. I'm doing a prograde burn, making our orbit more elliptical, and as a result, it's telling me that if I were to cut my engines now, it's telling me that if I now coast around over here to this side of our orbit where the descending node is, it's going to take 334.9 seconds to align our orbital plane with mirror, compared to 516.5 seconds at the ascending node. So you can quickly see by changing the shape of your orbit, you can directly impact the amount of fuel and time it's going to take to align your orbital plane with a target. However, obviously we used fuel changing the shape of our orbit, and we'd have to use fuel again to recircularize our orbit. So you sort of have to weigh the benefit of the cost savings. Is it worth changing the shape of your orbit in order to save fuel on the aligned plane? Another thing that you could consider is timing your orbit maneuvers so that you maximize your fuel efficiency. So for example, let's say that perhaps there's another vessel in high orbit that we wanted to rendezvous with, but we needed to both increase our orbit altitude to match that of our target and also align our orbital plane. So let's say that the vessel we wanted to rendezvous with is up here at this altitude. So if I had done a burn over here just like I did at the ascending node or either one of the nodes and increased our orbit altitude on the other side of the planet to match that of our target's altitude, and doing so at the node, that decreased the amount of time that we would have to burn our main engines to align our orbital plane. So we could coast over here, align our orbital plane, taking advantage of the decreased time it would take to do so, then coast back around the planet over here again to our apoapsis, and do a prograde burn to circularize the orbit up here at this high orbit altitude to match our target. So it's a little bit of an in-depth description, but it gives you an idea. The main thing that I wanted you to take from this is that by changing the shape of our orbit, and specifically doing so at one of our nodes, we can decrease the amount of time and fuel it takes to align our orbital plane with the target. So that is how you align your orbital plane, the breakdown of understanding what that involves. And that sets us up for the next part, which we will pick up from before I change the orbit and everything. We'll pick up with our orbital plane perfectly aligned with ISS. I saved that scenario, so we'll pick up there. And we'll learn how to set up an interception point and synchronize our orbit so that we can rendezvous with ISS. So as always, thank you guys for watching. Be sure to leave me a like, comment, subscribe for updates, and we will see you in the next video.